Building an electromagnetic motor, Group 1A. Introduction. Our goal for this lab was to understand how changes in the magnetic field and current of a circuit would affect the speed of a motor that was built using wires, batteries, and magnets. Our hypothesis is, as we increase the amount of current going through the circuit, the wire coil motor will spin faster. Our main findings were that as the amount of current flowing through the circuit increased, the speed of the electromagnetic motor increased as well. In this experiment, we can conclude changing the amount of current changes the speed of an electromagnetic motor. Our experimental design was set up, our motor was set up using model clay, magnets, wires, a wire coil, and batteries. The wire coil is stripped completely on one side and only stripped on one half of the other side, so that when the coil rotates, the circuit is broken at some points, meaning that the magnetic fields from the magnets and the wire coil won't ever line up and prevent the coil from spinning. To understand how a difference in the amount of current flowing through the motor changed the speed at which it spun, we conducted trials with 2, 3, 4, and 5 batteries. Current measurements were taken to show that current was increased due to an increase in the number of batteries used. We used slow motion video to count the rotations of the motor per second. Our limitations and sources of error could be from observations for the rotations per second were counted as from a slow motion video, which could leave room for error. And to obtain current readings, we had to break the circuit so that it may be slightly different from the actual current going through the motor. Our relevant models to this experiment revolve around Newton's second law, conservation of energy, and Lorentz force. Newton's second law states that the acceleration of a particle is dependent on the force exerted upon it and the mass of the particle itself. By increasing the amount of batteries in a circuit, the electric field is increased, thus acting as a larger force that is inducing the electron flow and increasing acceleration. Conservation of energy states that the total energy of an isolated system remains constant. Energy can only be transformed from one form to another form, or from one system to another. In the experiment, the system is a homopolar motor. As the electric energy flows through the circuit and comes into contact with the magnetic field surrounding the wire coil, it is converted into mechanical energy and heat. Lorentz force is the force exerted by a magnetic field acting on a moving electric charge. It is a combination of electric and magnetic force. Homopolar motors are driven by Lorentz forces. When a conductor with a current flowing through it is placed in a magnetic field that is perpendicular to the current, it feels a force in the direction of perpendicular to both the magnetic field and the current. This force provides a torque around the axis of rotation and allows for the wire coil to spin.
For our experiment, we assumed that increasing the number of batteries would increase the current. And as proven by the equation for a magnetic field, current is directly related to a magnetic field, so an increase in current will increase a magnetic field. As proven by the equation for the force of a magnetic field is directly proportional to the force, so as the magnetic field increases, the force increases. Force is equal to mass times acceleration, and if the mass is constant, as seen in our motor, acceleration must be increasing, meaning that the wire coil is going to spin faster, as we see in the rotation per second values that we have in our data. And because the force equation is a cross product, and the magnetic field and current must be perpendicular to make the wire coil spin, we can use the right-hand rule to find the direction of the force. For this experiment, our data included the rotations per second for each circuit we created, current readings, and the voltage. For each circuit, the rotations per second, current, and voltage all increased. From this experiment, we can see that our hypothesis is supported. Due to not having a way to measure the magnetic field, we are unable to calculate the change in the force. The graph shown here shows that as the current in milliamps increases for each circuit, depending on the number of batteries that we have in the circuit, the rotations per second of the wire coil also increase.